So let's switch gears just a little bit. In our last video, we looked at Raleigh's theorem. The other half of this section covers the mean value theorem, which is similar to Raleigh's. So Raleigh's is used to prove a value where the derivative is equal to 0, whereas the mean value theorem tells us there's some place where the derivative is equal to the slope of the secant line connecting the endpoints of the interval. So easier to sort of visualize when you look at the graph. Let's say these two are my two endpoints, and whatever this slope is would be the same as this slope up here. So there's some point in between those 2 points where the tangent line, the slope of the tangent line is equal to slope of the secant line that would connect the endpoints of my interval. So let's take a look at a mean value theorem application. We're going to verify that the mean value theorem applies to our function f of x equals 3 minus 5 over x, and then find all of the values of c which satisfy the MVT on the interval from 1 to 5. Now, just like we did with Raleigh's theorem, we have to verify that we can even use the mean value theorem. And our conditions are much the same as Raleigh's, without number 3 that used to say f of a must equal f of b. We don't need that for mean value theorem, because if f of a equaled f of b, then we'd be using Raleigh's and not mean value. So mean value, again, we're looking for where is the slope going to equal the slope of the derivative. So let's take a look. F of x is continuous on 1 to 5. So if I'm looking at this function, you might be thinking, hold up, that's not a continuous function, and you're right. We know that x cannot equal 0, otherwise it's not continuous. But because I'm looking at the interval from 1 to 5, we're okay. So it is both continuous and differentiable over that interval. Notice that the derivative of this is 5x to the negative 2, or 5 over x squared, so that's going to be my derivative, f prime of x. So the difference between the mean value theorem and Raleigh's theorem is in Raleigh's we just set the derivative equal to 0 because we were looking for a slope of 0 of the tangent line. Here I'm looking for a slope of, well, the secant line, which I haven't figured out yet. So I've shown all of the work here, but I'm going to sort of break it down for you a little bit. Remember that I'm using the points 1 and 5. So really I plugged in f of 1 into my original function, which would be 3 minus 5 over 1, and that's what I have here. 3 minus 5 over 1 would be negative 2, and then I plugged in 5, which was the other endpoint, and that would be 3 minus 5 over 5, which is 3 minus 1, which is 2. So that was this guy. So really, that's all I did here is I found the y values, and so now I'm using the slope formula. So f of b, 2, minus f of a, negative 2, that's here, over 5 minus 1, which is a, or b minus a, 5 minus 1. On the left side, notice what I'm using is not 0 or anything. I'm using the derivative. So before, if I was using Raleigh's theorem, I would have this equal to 0. Now I have this equals to whatever the slope is of the secant line, which I haven't fully computed yet. So again, then I get negative 2 minus negative 2, which is 2 plus 2 over 4, which is 1. So this is the function that I'm solving. Then I multiplied each side by x squared. I divided each side, or sorry, took the square root of each side to find plus or minus radical 5. Now that's two answers. Negative radical 5, positive radical 5. Notice I'm looking at the interval 1 comma 5, so this guy doesn't exist in that interval. So basically I've proved that the mean value theorem applies by checking those conditions and then finding all of the values of c, and so c would have to be only radical 5 because radical 5 does fall in the interval, and we know that the slope is equal to the derivative. Here's another example, and again, if you don't feel comfortable enough yet to do this on your own, You don't have to. You can just work through it with me. But if you feel like you're ready to try it, or at least try a couple of parts of it, feel free to press pause and do all of the parts. There are 2 other parts on the next slide, so just try to focus on these 2. And then we'll go over them, and then we'll do the rest of the question on the next slide. So here we have a function f of x equals negative x squared plus 5. So first thing we're going to do is find the equation of the secant line that joins the 2 points, negative 1, 4, and 2, 1. So this is just algebra. That's an easy one. How am I going to find the equation of the secant line? I'm going to find the slope, y2 minus y1 over x2 minus x1, find a slope of negative 1. I'm going to use point slope formula, which we use all of the time, to then find my equation in slope-intercept form. Using either one of these 2 points, obviously I used the point 2, 1, but you could have used the point negative 1, 4 and still had the same equation. Part B says use the mean value theorem to determine a point C in the interval, negative 1, 2, such that the tangent line is parallel to the secant line. So before we get crazy, let's determine what they're asking. We have already determined that the slope of the secant line is negative 1. So what they're saying here is find some point C between negative 1 and 2 that has a slope of a tangent line of negative 1. So how do I do that? Well, first I have to say that I can use the mean value theorem because the function is continuous and differentiable because it's a polynomial. Then we can say, let's find f prime of x. So we're differentiating our original function to get negative 2x. Just like in our last example, I'm going to take my differentiated function and I'm going to set it equal to the slope of the secant line. So notice I've just said negative 1 is equal to negative 2x and solved. So x is equal to 1/2. So let's do the other 2 parts. Again, if you're feeling good about yourself and you feel like you can conquer the last 2 questions, feel free to do that. If you're still just following along with me, that's fine too. We're going to go ahead and get started. Just as a reminder, since I didn't recopy that information on this page, from part B, what we had just determined, well, from parts A and B, is we determined that the slope of the line is negative 1, and that's the slope of both the secant line and the tangent line that we're trying to find. And we also determined that the x value at which our tangent line would have a slope of negative 1 was 1/2. So that's what we just determined in our last question. Now they're asking us to go ahead and find not the point where the line would be, the tangent line would have a slope of 1, but the actual equation of the line. So what does that mean? More algebra? Of course. Here we are finding a point on that line, because we know in order to find the equation of a line, we either need 2 points or we need the slope and a point. So I have the slope, thankfully. All I need is 1 more point, and that point is going to occur where x is equal to 1/2, but I don't know what y is equal to. So notice I've taken that original equation, which was negative x squared plus 5. So that's my f of x, not f prime of x. And I'm plugging in 1/2 because that's the value that I determined in B. And doing all of that math, I found 19/4. So now I'm using point slope form, using my slope of negative 1 right here, and then my point of 1/2 comma 19/4 to find the equation of the line. So to recap before I graph it, I have found the slope of the original graph, the secant line, sorry, the slope of the secant line of the original graph. I have also found the slope and equation of the tangent line at the point 1/2 comma 19/4. Now, if you'll notice, I did this in Desmos, what I have done is I have found using the points, or using the interval, which I believe was -1 to 2, I found that this slope was -1. And remember, I was looking for the point in this interval from here to here where the slope, well, I guess from here to here, where would the slope of the tangent line also be -1? And if you'll notice, this equation is this guy right here. That slope is -1 as well at the point 1/2, comma 19/4. So I've basically verified everything that I've done. I do have a practice worksheet for sections 3.1 and 3.2, which is of course extrema, mean value, Raleigh's theorem, etc., all of the above. It's great practice, and again, it's a way for you to collaborate with your classmates. So if you take the time to do those questions, I'll take the time to look over them with you.